The Irish government invests money from the National Pension Reserve Fund at 6% per annum. What sum must it invest now to repay €3 billion in a year's time? We are interested in the present value of 3 billion. Now 3 billion is 3,000 million, or 3 times 10 to the power of 9. So we want to see what sum of money will amount to €3 billion after 1 year at 6% per annum. So it's a year's time. So t is equal to 1. R is equal to 6. So in here we have 1 plus 6 over 100, 1.06. To the nearest integer we get 2,830,188,679 euros. So if the government invests this amount of money right now, it will grow to 3 billion euros in 1 year's time. The Irish government has to pay off, as part of its bank recapitalisation programme, a debt of 25 billion euros in 10 years according to the schedule in the table below. How much money must be invested by the government now from the National Pension Reserve Fund to pay off the debt of 25 billion euros in 10 years' time at 6% per annum? So this table means that at the end of each year we have to pay off this amount of money in billions. So at the end of year 1, 3 billion has to be paid off. At the end of year 2, another 3 billion has to be paid off, and so on. All of these numbers add up to 25 billion. So we need to get the present value of all of these numbers. So we can start with 3 billion at the end of year 1. What is the present value of that right now? Well, we know from the previous part that it is 3 billion divided by 1.06 to the power of 1, or just 1.06. We're just dealing with 1 year here. And we calculated this to be 2.83 billion roughly. Now I won't write in 3 billion, I'll just use units of billions. Next we get the present value of 3 billion euros after 2 years. Well, the present value formula tells us that that amount is the amount at the end of 2 years, which is 3 divided by 1 plus r over 100 to the power of 2. So it's going to be 1.06 to the power of 2. So this gives us the present value of 3 billion euros in 2 years' time. And of course we have to add it on to the present value of this. We want to get the present value of all of these. Similarly, the present value of 3 billion euros after 3 years is going to be 3, the amount after 3 years, divided by 1.06 to the power of 3. So the t is equal to 3 in this situation. Similarly for years 4 and 5. So paying off 3 billion euros at the end of year 1, another 3 billion at the end of year 2, another 3 billion at the end of year 3, and so on up to 3 billion at the end of year 5 is equivalent to paying all of this amount here right now, because all of this here will amount to these numbers, that is 15 billion. But of course we have to deal with these extra numbers. So we want the present value of 2 billion at the end of 6 years. So we want to get the sum of money that amounts to 2 billion. So the amount is 2, and that's divided by 1 plus r over 100 to the power of t. Well, the rate is still 6%. The rate is 6% every year, and t now is 6. And similarly for year 7, the amount is 2 billion. We want to get the present value of 2 billion euros in 7 years' time. And so on for the next 3 years. So at last, if we pay out this amount of money, whatever it is, we'll calculate it soon, it's equivalent to paying out all of these amounts at the end of each year for the next 10 years. So we could just do one big payment now. Well, it's not so much a payment, it's invested, of course. And this amount will mature to 3 billion at the end of year 1, so that we can pay that off. This here will amount to 3 billion after year 2, so that takes care of that amount, and so on. So when we invest this amount of money, we will be able to clear the debts in this fashion here, shown in this table, and so on. Now you could just plug all this into a calculator, but I just want to explain something about this expression here. We've got two geometric series together. So this part here is a geometric series. I'll just deal with this part first. The first term, which is normally denoted by small a, is 3 over 1.06. The common ratio, which is denoted by r, this r has nothing to do with interest rate, of course. It's just a term, it's just a letter used to denote the ratio between consecutive terms. So if we take, say, the second term and divide by the first term, we can calculate r. So here I'm taking t2 and dividing by t1. This is 1 divided by 1.06. It's pretty clear that r must be this, because if we multiply 1 over 1.06 by the first term, well, we'll get 3 over 1.06 squared. And if we multiply the second term by this, we get 3 over 1.06 cubed. So we're not affecting the numerator, but we're increasing the power of the denominator by 1. So we have a geometric series, as I said already. And how many terms do we have? Well, we have 5 terms. And we can use a formula for summing a geometric series to calculate what's inside the red brackets. So here's the formula. This is covered in the section on geometric series. So a is 3 over 1.06. r is 1 over 1.06, so I've just plugged in. And we're getting S5 here, sum of the first 5 terms. That's what this is. So n is 5. Similarly, here we have another geometric series. This time the first term, which I'm calling a, is 2 over 1.06 to the power of 6, or the common ratio is actually the same as for the other series. It's 1 over 1.06. n is 5, we have 5 terms. So the sum of the first 5 terms is given by this formula here, of course. So we just plug in. Notice that these are very similar, except for the 2 and the 3. We have to add these together, of course. Actually, the power here is different as well. I forgot to mention that. That's a 6. This is just a 1. When I add these together, I can actually factorize out this thing here. This expression is common to both of these. And what's in front can be added together. So I can add this onto this. That's what I have here. And multiply by what's inside the square brackets. So I'll plug this part in first. We have 1 minus 1 divided by 1.06. This thing is raised to the power of 5. So I divide by that by 1 minus 1 divided by 1.06. So now I have to multiply this by this quantity here. So remember, these units are in billions. So to one decimal place we get 18.9 billion.